Hello, welcome to the DataFest 2020 Uncertainty in Machine Learning track. My name is Andrey Malinin, and today I will tell you a little bit about uncertainty estimation, and specifically we'll focus on the questions of why uncertainty estimation is important and where uncertainty comes from. Let's focus on the first question. So philosophically speaking, intelligent agents must understand the limits of their knowledge. Animals will display fear and curiosity, they will explore new environments, they will act anxiously when facing situations they haven't faced before. Humans can ask questions, weigh risk and reward, and in general make decisions under uncertainty. In general, uncertainty or estimates of uncertainty must affect the actions of an intelligent agent. If an intelligent agent is uncertain, then he or she may not take an action which is particularly risky. For example, in the situation of a global pandemic, perhaps buying a new apartment when your income is not assured is a poor action. So uncertainty estimation is important in these cases at a very global level. Now we can also discuss a more practical aspect of uncertainty estimation. Machine learning systems have been deployed to many applications like image classification, speech recognition, machine translation, dialogue systems, medical, financial applications, and autonomous vehicles. Now, in some of these applications, the cost of a mistake can be high, for example, in terms of reputation, money, or the consequences can simply be fatal. For example, over the last 4 years or so, there have been 5 fatal car crashes with autonomous vehicles. 4 Tesla cars have crashed and 1 Uber car has crashed. And this is unfortunate, and we'd like to avoid these situations. Another example was when an Irish woman was taking an English language test in Australia. In Australia, there was an automated system for exam assessment. However, it was trained on Australian speakers of English, and despite the fact that the Irish woman spoke English perfectly, she had a different accent and the system thought she spoke English poorly. These are examples of situations where autonomous systems, where machine learning makes mistakes, and we'd like to use estimates of uncertainty to avoid these mistakes and thereby increase the safety and reliability of the systems we deploy in practice. Now, the typical usage scenario for uncertainty is as follows. We have a deployed model and it receives some kind of test input X. This could be audio, this could be images, this could be text, it doesn't matter. For this input, we'd like to obtain the prediction. The car drives somewhere, or gives us the next word, or predicts the price of Bitcoin, and so on and so forth. Additionally, we'd like to obtain a measure of uncertainty in this prediction, which tells us how sure the model is that the prediction is correct. And based on the prediction and the estimate of uncertainty in the prediction, we'd like to take an action. Either reject the prediction, accept the prediction, stop decoding a sentence, modify our reinforcement learning policy, do extra exploration, maybe ask for human intervention, or perhaps deploy active learning. The action really depends on the application of interest. So, having established that uncertainty is important in order to increase the safety of systems and avoid mistakes, we now have to examine the question of where uncertainty comes from. Why can systems be uncertain in general? Now, in general, there are 2 sort of idealized sources of uncertainty. One is data uncertainty and the other one is knowledge uncertainty. Data uncertainty is often also called aleatoric uncertainty, and knowledge uncertainty is often also called epistemic uncertainty. However, we'll stick to data and knowledge because, in my opinion, these are slightly more clear terms than aleatoric and epistemic. So let's focus on data uncertainty. We'll use this synthetic example with 3 classes to describe the situation. So imagine you have 3 Gaussian distributed classes. Let's say they stand for the digits 1, 2, and 3, for example, or anything really. Now, in this particular case, the classes are non-intersecting, and the green test point can clearly be attributed to the second cluster, or the second class. However, if the points are intersecting, we can no longer tell to which class the green dot belongs. Maybe it's class 2, maybe it's class 3. So in this area of the input space, the features of the green dot have attributes of multiple classes. The classes are overlapping in this region, and we cannot tell apart which class it is. So examples of this on hand-drawn digits is, for example, On the top you have the digits 1, 2, and 7 drawn distinctly. They're easy to separate. On the bottom you have the digits 1, 2, and 7 written in a very messy way, so such that they are hard to discriminate. This is an example of data or aleatoric uncertainty. In general, data uncertainty is when you have for classification, data uncertainty is when you have two or more classes which are overlapping and you cannot distinguish it. Just like this cat dog, it's both a cat and a dog, but it's neither. This is data uncertainty for classification. Now for regression, it takes the form of additive noise. So let's say you have some underlying function you're modeling. For example, sine 2x plus x over 10. Then we add to this underlying function noise which has Gaussian noise, zero mean Gaussian noise with a standard deviation which is a function of x, as defined in image B. So sigma x equals 0.02 plus 2 over modulo of x squared plus 1. So this defines the true level of noise. And if we sample data from this distribution with mean as defined in image A and standard deviation as defined in image B, we'll have the data points described in image C on the right. So clearly, in the center around 0, all the data points are highly noisy and it's difficult to make out the underlying function there, even though the underlying function is still sine 2x plus x over 10. Now this additive noise is data uncertainty for regression. Now this additive noise can be homoscedastic or input independent, where sigma x takes some constant value. Or it could be heteroscedastic or input dependent noise, where the level of noise depends on the input. There's some function, for example, 0.02 plus 2 over x squared modulo plus 1, which describes the level of noise. Now, all of this discussion doesn't talk about any models. We're talking about the data, the underlying data itself. Data uncertainty is a property of the data. So, now we've discussed data uncertainty. Now let's talk about knowledge uncertainty. So knowledge uncertainty is now a property of the model. And it pertains to regions which are either out of distribution relative to the training data, or regions which are sparsely covered by training data. Let's focus on the first case. So here you have with the red points, they represent our training data, and in this region we understand the nature of the inputs and so on and so forth. But we receive a test input which is very far from the training data. And in this region we have no training data. We don't know anything about this region of the green point. It could be a new class, it could be the same class, it could be maybe one of the other classes. We don't know because we have no training data there. So our models, whatever they are, can make mistakes, which are either very big or very small, but they can very, very likely to make mistakes far from the training data. This is an example of dataset shift or out-of-domain inputs or anomalous inputs. You can describe this in many ways. But the point is that the test data comes from a different distribution to the training data. A less extreme example is when the test data comes from a region which is sparsely covered by the training data. So here we have two classes which have very many data points, I think 1,000 in this image, and there's the third class which has 10 data points. Clearly, in the region of the third class, we understand this area far worse than the other two classes, and we can misestimate decision boundaries, maybe make mistakes. Maybe they won't be as great as in the previous example, but we can still make mistakes in regions where we have very few training examples. Now, this is an example of knowledge uncertainty. A more concrete example of knowledge uncertainty is as follows. So on the top, we have an example of unseen classes or new classes. On the top left, we have the MNIST datasets, which I'm sure you are all very familiar with. It covers the handwritten digits from 0 to 9. And then on the right, we have the omniglot dataset, which covers handwritten characters from very many different alphabets. Now, clearly, these characters represent different classes, which are not seen in MNIST. And our model simply can't classify them correctly at all because it's never seen anything like it. Although some characters can look similar to certain digits, like the 9 and the 9-looking character in omniglot. That's a very extreme version of knowledge uncertainty. Now, on the bottom row, we have examples of this sort of data sparsity issue. So on the bottom left, we have examples of 1 and 7, where 1 is drawn as a single line and a 7 doesn't have a crossbar. And let's imagine that we've only seen 1s and 7s like this. Suddenly we have test inputs, which are 1s and 7s, but 1 has a little hat and the 7 has a crossbar. Now, in this case, our model may confuse the 1 with the hat with the 7 without a crossbar, because it's never seen a 7 with a crossbar. Or maybe it'll generalize appropriately based on the shape of the remainder of the 7. We don't know what will happen, but in general, this represents a situation where the model can make mistakes because it has seen very few variations of these classes, because the training data covered these particular regions sparsely. Now, an extreme example of knowledge uncertainty, which I think is fun to do in a real live lecture, is to show people this Rorschach test. So this image comes from a Rorschach test, and typically people are asked what they see here, and people can say many different things: an angel, a demon, a child with wings and a burning head with flying raspberries around it. It doesn't matter. People will say very different things. Somebody will say goats, 2 goats butting heads or something. The point is, this image doesn't represent anything, but at the same time, if you ask different people, they will say different things, because this image is out of distribution for every single person, and they will say things which are consistent with their own internal, quirks of their minds, the associations, and so on and so forth. Similar things will happen if we ask different models. And this will become very important when we talk about how to estimate knowledge uncertainty in the next lecture. So some more examples to give you a feel for what data and knowledge uncertainty are. So for example, in speech recognition, when you enter a noisy room or a room with lots of speakers, echo, and so on and so forth, making it very hard to understand speech, this is an example of data uncertainty. In machine translation, often a sentence can be translated in very many different ways. The distribution is fundamentally multimodal. Or the next word, there are multiple possible next words in a translation. For example, synonyms. These are examples of data uncertainty. In object segmentation, often you have data uncertainty at object boundaries, because the boundary may belong to one object or a different object. You don't know which object exists because it's on the boundary. And finally, in regression cases, let's say you're taking measurements of somebody's temperature and there's noise in the measurement. That's also data uncertainty. Now, knowledge uncertainty for speech recognition or translation would be if somebody is speaking a foreign language. Let's say you're in a very quiet, nice room, no echo, very good acoustic conditions, but the person speaks a language you don't understand. Let's say Sanskrit or Latin or some other dead language, Minoan. And you just don't know, and you just don't understand what is being said. That's knowledge uncertainty. For segmentation is an unknown object. For image classification, an unknown object. For depth estimation, it could be a new environment, and so on and so forth. In general, knowledge uncertainty represents various forms of dataset shift and data sparsity problems. So, summarizing, data uncertainty represents a form of known unknown. We know regions which have high data uncertainty, such as regions of class overlap or regions of high homoscedastic or heteroscedastic additive noise. But our model understands that it can't give accurate and dependable predictions in this region. Knowledge uncertainty is a form of unknown unknown. It represents uncertainty due to dataset shift or due to a region of the input space being sparsely covered by training data or not covered by training data at all. It's a form of unknown unknown because we don't even know that we don't understand this region, because we have nothing to tell us that this region is different. Now, like a reality check, which we have to have, is that data and knowledge uncertainty are idealized sources. Real data in real data sets and real problems you will encounter has a little bit of both. Some examples may be noisy, but a little out of domain. Some examples may be very out of domain, but not noisy. In general, you will have an overall level of total uncertainty, which is derived from both a level of data uncertainty and a level of knowledge uncertainty. Now, the reason we care about separating these two sources is that an appropriate action depends on the source of uncertainty. So, for example, if we are trying to detect errors, we care about total uncertainty because it doesn't really matter why we're making an error. All that matters is that we are uncertain in the prediction we're making. But if, for example, we're trying to do anomaly detection or doing active learning, where it's important to collect new training examples which we haven't seen before, we need to look for examples with a high level of knowledge uncertainty. So thank you. This brings us to the end of our first video. Hopefully you've enjoyed it and learned something cool, and stick around for the next one. Thanks.